I'm going to turn you loose on this one. We have 4x squared y double prime plus y is equal to 0. And because we have this term that contains x squared and y double prime, right? The exponent on x matches the order of derivative on y. And there is no x on the y term. This is a Cauchy-Euler equation. Remember that the form of solution for a Cauchy-Euler equation is y equals x to the m. Using that, I'd like you to pause the video and solve the differential equation. We have that y prime is mx to the m minus 1, y double prime is m times m minus 1 x to the m minus 2. Multiplying that y double prime by x squared is going to give us a term that is 4m m minus 1 x to the m. And then for y, we have x to the m. Those add up to 0. The auxiliary equation, 4m squared minus 4m plus 1 is equal to 0. Factors, 2m minus 1, the quantity squared, equals 0. We have m equals 1/2 repeated. And y equals c1 x to the 1/2 plus c2 x to the 1/2 natural log of x. I don't generally write things like this as natural log of x times x to the 1/2 because then it's not really clear if the argument of x includes that x, or the argument of the natural log includes that x to the 1/2. You could put parentheses around the x, but then y? You can just put it in front. So that's generally the order in which I'm going to write terms like that. Next up, x squared y double prime minus 7xy prime plus 41y equals 0. Again, when we have the second derivative of y, we have the factor x squared. The first derivative of y, we have the factor of x. And then for the y term, we have no x. This is a Cauchy-Euler pattern here. Again, starting with y equals x to the m, I'd like for you to do all the things and solve this equation. Let's see if we match. Y prime is mx to the m minus 1. Y double prime is m times m minus 1 x to the m minus 2. That seems to keep being the case, doesn't it? Multiplying x squared by that y double prime is going to give us x to the m. It's, by the same token, multiplying x by x to the m minus 1 for y prime's term is going to give us x to the m. You have x to the m's everywhere. I'm jumping to the auxiliary equation. M times the quantity of m minus 1 minus 7m plus 41 is equal to 0. So doing a little bit of manipulating here, m squared minus 8m is equal to negative 41, and completing the square means adding 16 to both sides, so I get m minus 4, the quantity squared, is equal to negative 25, so m is equal to 4 plus or minus 5i. The real part is going to become the exponent on x. The 5 is going to become the coefficient in the argument of the sine and cosine, and don't forget, because it's Cauchy-Euler, the sine and cosine also contain a natural log of x. So y equals x to the 4th times the quantity of c1 cosine 5 natural log of x plus c2 sine 5 natural log of x. A Cauchy-Euler equation can actually be converted to an equation that has constant coefficients using the substitution x equals e to the t and the chain rule. And I'll offer a rationale for that statement. The general solution to ay double prime plus by prime plus cy is equal to 0, where a, b, and c are constants, is, as you know, y equals c1e to the m1x plus c2e to the m2x, where m1 and m2 are solutions to an auxiliary equation. I'm going to star that equation because I'm going to reference it in just a moment. The general solution to ax squared y double prime plus bxy prime plus cy equals 0, again, where a, b, and c are constants, is, again, as you know, y equals c1x to the m1 plus c2x to the m2. But because of properties of logs and exponents, x is e to the natural log of x using cancellation property, which means that x to the m1, for instance, is e to the m1 times the natural log of x. And so that first solution that we wrote down becomes y equals c1 e to the m1 natural log of x plus c2 e to the m2 natural log of x. If we let x equal e to the t per the substitution in the statement above, then we get y equals c1 e to the m1t plus c2 e to the m2t, which has a form that resembles star. So you can kind of see why natural log of x was showing up in the examples in this section. There's nothing like seeing this actually in action. So here we're going to use the substitution x equals e to the t to transform a Cauchy-Euler equation to an equation that has constant coefficients, and then solve the original equation using the new equation. And our equation is x squared y double prime plus 9xy prime plus 25y is equal to 0. Since x is equal to e to the t, that gives us that t is equal to the natural log of x. The solution that we're seeking is y, which is a function of x. And we get that y is a function of x becomes y of t of x, inserting essentially t in between y and x, with t of x being the natural log of x. Now we're going to do some substituting. We need to substitute y prime and y double prime. Y is t of x. We're going to differentiate with respect to x. dy dx is dy dt times dt dx using the chain rule. We know what dt dx is though, because t is natural log of x. This thing becomes 1 over x times dy dt, where the 1 over x is coming from dt dx and t is natural log of x. The next step is requires a bit of thought. d2y dx2 is the derivative with respect to x of 1 over x times dy dt. This derivative requires the product rule. We're differentiating with respect to x, remember. The derivative of 1 over x with respect to x is negative 1 over x squared. dy dt, that's the first part of the product rule. The second part is 1 over x times the derivative with respect to x of dy dt. And for that term, we're going to end up with the second derivative of y with respect to t times dt dx, which is another 1 over x. So finally, d2y dx2 is negative 1 over x squared dy dt plus 1 over x squared d2y dt2. We can factor a 1 over x squared out of that thing. We have d2y dt2 minus dy dt. All of that is going to replace d2y dx2 in the original equation. Notice, the term that has y double prime has a factor of x squared. That x squared is going to multiply by this 1 over x squared, and it'll divide out. Likewise, the y prime term has a factor of x in it, negative 9xy prime, and dy dx, which is y prime, has a factor 1 over x. So the x's are going to divide out. The result is the equation d2y dt2 minus dy dt minus 9 dy dt plus 25y is equal to 0. Notice all of our derivatives are derivatives of y with respect to t. Combining some like terms here, d2y dt2 minus 10 dy dt plus 25y is equal to 0 gives us an auxiliary equation. M squared minus 10m plus 25 is equal to 0, which gives us that m is equal to 5 repeated. So y is equal to c1 e to the 5t plus c2 t e to the 5t. Remembering that t is equal to the natural log of x, we find that y is equal to c1 e to the 5 times the natural log of x plus c2 natural log of x e to the 5 times the natural log of x. And 5 becomes the exponent on x, e to the natural log offsets each other, or they cancel out, and we end up with y equals c1 x to the 5th power plus c2 x to the 5th power times the natural log of x. So now you see where that natural log of x is coming from, and hopefully that x to the 5th power is making sense for the other examples that we saw in this set of videos. A final piece of information for Cauchy-Euler equations. Here we have our case 1, case 2, and case 3. All of these are for the homogeneous case. For the non-homogeneous case, where we have ax squared y double prime plus bx y prime plus cy is equal to g of x, we first put this into standard form, which of course looks like y double prime plus p of x y prime plus q of x y equals f of x, and then use variation of parameters.